Let us now discuss the superposition of the ideal sinusoidal wave. Okay. If we have two sinusoidal waves which represented by the wave function y1 equal to a sine omega kx minus omega t, okay, and the second wave y2 equal to a sine kx minus omega t plus phi. Okay. For the simplicity, we assume here that these two waves have the same amplitude. Okay, have the same amplitude. This is not the general situation, but it makes the calculation easier. We also give the phase difference of these two waves with this parameter phi, okay, to make this wave different. I mean, to make the phase of these two waves different. But other than this, they are identical. Okay. So, if these two waves move in the same region, so we can have the superposition of these two waves of two waves. Okay, y is equal to y1 plus y2, which equal to a sine kx minus omega t plus sine kx minus omega t plus phi. Okay. Now we can use the trigonometric identity to sum up these two sine functions. We have that sine of A plus sine of B is equal to the 2 of cosine of A minus B over 2 times sine of A plus B over 2. Okay, so in this situation, if we choose this term to be A, and we choose this term to be B, and also use the fact that cos of minus theta is equal to cos of minus theta is equal to cos of theta. Okay, so we will have the resulting wave as y equal to y1 plus y2 is equal to 2a cos phi over 2 sine kx minus omega t plus phi over 2. Okay. This is the result of the superposition of the wave number 1 and number 2. You can see that we still have the traveling wave because we have the term sine kx minus omega t, but the phase constant change, it becomes phi over 2. But what is the most interesting here is the amplitude of this wave, this term. It is a function, the cosine function of the phase difference phi over 2. We can see that if phi is equal to 0, we have that cosine of phi over 2 is equal to 1. So it means that the amplitude of the wave of the resulting wave is equal to 2a, which means that 2 times the amplitude of each wave. So we say that this is a perfect constructive interference, the perfect constructive interference. If we draw the graph, or if we look at the snapshot of the wave number 1 and number 2, we will see something like this. For the first figure, this figure, since phi is equal to 0, which means that two waves, y1 and y2, are truly identical. So if you take a snapshot of those two waves, it will indistinguishable. It means that the oscillation of the medium of each wave will be identical, and you will see only one curve for those two waves. And it means that when the wave number 1 oscillate up, the wave number 2 also oscillate up, and the displacement is the sum of these two of the displacement of those two waves. And when those two waves oscillate down, we have the displacement down like this. So this is a perfect constructive interference. The amplitude, the resulting amplitude is the addition of the amplitude of each wave. Okay. Now let's go back to see the we may say that the opposite situation. That is, if we have that phi is equal to pi. Okay, if phi is equal to pi, we have that cos of phi over 2 is equal to 0, because cos of pi over 2 is equal to 0. So it means that the amplitude of the resulting wave is 0. The amplitude is 0. So the resulting wave vanish. We don't have the wave anymore if these two waves have the phase difference equal to pi. And we call this situation the perfect destructive. The perfect destructive interference and we can have the situation like in this second figure. You can see that since the phase of these two waves are pi or 180 degrees, when the first wave oscillates, or the displacement from the first wave is up, go up like this, the displacement from the second wave will go down. And when the displacement of the second wave go up, the displacement from the first wave go down. So you can see that the displacement of these two waves point in the opposite direction all time. And the displacement will cancel. And we have the resulting wave as nothing. Right? This is just a straight line because the blue wave and the green wave cancel each other, and we have this straight line. And this is a perfect destructive interference. What happened in between? If phi is between pi and 0, or between 0 and pi, we will have partial. We can say that it's partial constructive or it's partial destructive. That is, we may have that the resulting wave, the amplitude of the resulting wave may be greater than A, like this, greater than the amplitude of each wave, but not maximum. It's not equal to 2A like in the perfect constructive interference, but maybe greater than A. Or you can have that the displacement, the maximum displacement of the resulting wave is less than the amplitude of y1 of the wave number 1 and number 2. So if the resulting amplitude of the amplitude of the resulting wave is greater than the wave number 1 and number 2, but not equal to 2A, we call it a partial constructive. But if the amplitude of the resulting wave less than A but not equal to 0, it's a partial destructive.